Hi, this is Scott. I really appreciate our sponsors because they make the show possible. Today's show is sponsored by Developer Express. Become a UI superhero with Dev Express controls and libraries. Deliver elegant .NET solutions that address customer needs today. By leveraging your existing knowledge, you can build next-generation touch-enabled solutions for tomorrow. You can download your free 30-day trial at dx.hanselminutes.com. That's dx.hanselminutes.com. Hi, this is Scott Hanselman. This is another episode of Hansel Minutes, and today I'm talking with Thorsten Ball. He wrote an interpreter book and is a fan of compilers and interpreters and wants us to write one too. How are you?
Hey, Scott. I'm fine. How are you?
I'm brilliant, and I'm happy to be talking to you because you've self-published this great book called Writing an Interpreter in Go, and you can get it at interpreterbook.com. And it got me thinking about kind of the computer science that I learned in school and how it relates to the kind of the software engineering that I do today and every day. And it kind of begs the question, why would I want to write an interpreter or a compiler at this point in my career?
Right. So, my number one answer to this is always, you're probably not going to write a compiler or interpreter for work in a production environment, but if you dig into this topic, you're going to learn so much more about your tools, which are your programming language, your editor, your, IDE, than you ever thought you would. Because, once you learn about interpreters, you can suddenly understand where those memory leaks are coming from. You know what the parser error is. You know what an AST is. You know what the syntax tree is. You know how you would write a garbage collector. You know what compiling means, and you can suddenly start to build tools that you didn't think were possible for you to write before, once you realize that all this stuff is actually within reach and it's not that hard to do or hard to understand, and it's not some magic, because compilers have this image of mystique, and they're pretty hard to understand, they're complex, they're huge, and only certain people can write them. And I think that it's not something you're going to earn a lot of money with, in the sense that you're not going to be hired as a compiler writer, but it gives you a lot more leverage in your day-to-day job, where you probably work higher up the stack and use compilers and interpreters, because they're tools, you use them every day, and the better you understand them, the better you can wield them.
Mm-hmm. I remember the last time I wrote an interpreter was probably 20 plus years ago. And usually in the class, the teacher would give us some pretend language they would make up, and they would give us a spec for that pretend language. And then, as I recall, I used a tool called Lex and a tool called Yacc, Y-A-C-C. And I wrote the whole thing in classic C. We didn't even have C++ at that time. And for people just getting started in computer science, as I recall, it wasn't very fun, and it was very confusing. And once it was done, I forgot all about it. Right.
So, all right. I could talk about this for hours, but, this is actually the reason why I wrote the book, because it started with me being interested in writing interpreters or compilers. I set myself the goal. I'm a self-taught developer. I didn't go to college or university, and I didn't study computer science. So I never took the, compilers course. And I set myself the goal, and I said to a friend, I'm going to write a compiler. And what I found out is that all these resources, that teach you how to write a compiler or how to write an interpreter, they're pretty close to what you just described. People are always taking, shortcuts. They're saying, use this tool, use that tool, and don't write the parser yourself, and just ignore this part. You can skip this. You don't need to understand this. And, my favorite one is let's use an example language which looks nothing like any language you've ever used, and implement an interpreter for that, which can be super, super confusing. And this is the reason why I decided that if I'm going to write a book about this, or build a resource as a learning resource, I'm going to use a real programming language or something that looks like a real programming language. And what came out of it was a programming language called Monkey, which we implement in my book. And it looks fairly close to JavaScript. It has curly braces. It has first-class functions. It has a few different data types. It has strings, booleans, arrays, hashes, hash maps. And it looks like a real programming language. And there are no shortcuts in the book. So I decidedly said, we're going to write our own parser. And we're going to write our own lexer. And we are not going to use lex and yak and use the 30-year-old tools with, the only documentation is the man page in a Unix system. And we are not going to use them to implement our language, but we're going to build everything from scratch. And this is going to take a lot of time, but we're going to do it bit by bit, and we're going to learn a lot. And in the end, we're going to have an interpreter that's, I think 3,000 lines of code, maybe. It's fully tested, and we understand every line of it. So that was my intention, because as you just described it, it's super frustrating to always been, blindly led around and around stuff and told you have to ignore this, you can skip this, you don't need to worry about this, because as a beginner, you need to understand something, you need to grab a hold of something. And most people actually say that the most people learn the best way by giving straight recipes in the beginning. If you're an absolute beginner, the best is you have a recipe that takes you from A to Z, and you just have to follow it step by step without any, complex, abstract explanations about the topic in general and stuff like that.
Mm-hmm. Do you think that people are out there in the world writing their code and just trusting these black boxes? And for most people, the code goes into a compiler and then a miracle happens and then their executable pops out the other end and they truly have no concept of what happened in the inside.
Sure, of course. At the end of the day, that's part of the job. You can't go chasing every black hole. You can't keep digging, you can't just jump into every rabbit hole and see what comes out at the other end. If you do that, you're never going to stop, because computers have grown so complex over the years that it's impossible for any person to understand all of it. You can't understand the whole stack. And that's been true for the last, 20 or 30 years, maybe. Mm-hmm. So you have to stop somewhere. But again, the point is, if you understand some of it at the lower level, you can leverage that further up. But you have to know where to draw the line. Once you start thinking about compilers or interpreters, you're suddenly thinking about intermediate languages, and then you're starting to think about assembly language. And if you're down at that level, it's just a short step away to think about CPUs and how they are built. And then you start thinking about machine code, and then you realize that machine code is just the result of other code, and it can contain bugs too, and your CPU can contain bugs. And, you suddenly get dizzy and you have to sit down and you realize, oh, maybe this wasn't so easy after all. That's probably where you have to draw the line once you get dizzy. You have to stop somewhere. But I think, what kind of plays into this topic is this whole thing about leaky abstractions. Some abstractions are so good that you actually don't have to worry about any of it. And I'd say most relational databases are just like that, because you have to, you can just tell them what to do via SQL and they get your results back, and you don't have to worry about the storage engine, and you don't have to worry about how an index is, wrote to disk or something. And there are other abstractions where, they fall on your feet someday. For example, the first example I could think of right now is a graphical Git client, where you sometimes click around and you want to merge stuff, and suddenly it says, merge conflict, and it drops you back into your shell or your text editor, and suddenly presented with the merge conflict text, and you have to fiddle around with that, and the abstraction broke down. And in that instance, it's better to know one level below the one you're working on, which is kind of a general rule I try to follow. So, always know one level of abstraction below the one you're working on, meaning if I work as a web developer and I write web applications with language X, I should probably know a little bit about how this language works, what kind of memory model it has, how it's run in production, and how to deploy it, because most things like that are not just fire and forget, and you can throw them over the wall and don't worry about it, especially nowadays, where you have like small agile teams that do a lot of different things. And then it's good to always know which tools you're working with and how to work with them and how to manipulate them and how to get the most out of them.
Yeah, that really resonates with me. In a lot of my talks and when I'm teaching people computers, I always let them know about the abstraction layer, as you said, one below.
Right.
Like, for example, I use examples like, you're driving a car, and when you turn the steering wheel, do you know the relationship between the steering wheel and the actual wheels that touch the ground? And I was trying to teach a relative recently how to parallel park. And it turns out that they thought when you turn the steering wheel, all four wheels of the car turned.
Right.
And when they tried to apply that misunderstanding of that layer of abstraction to parallel parking, they were unable to accomplish that. So we stepped out of the car, talked about that one layer down in the call stack. Then the light turns on. They never have to think about it again. They just go back up to the higher level of abstraction. But by peeking underneath and understanding how the car works, they suddenly become a better driver. And it sounds like you're saying the same thing. Go and write an interpreter, write your own lecture, your own parser, and then you can go back to writing your web applications. But you're going to have all kinds of little Tetris pieces in your brain that have then been filled in with the knowledge of what's happening underneath.
Exactly. That's the main point, that you suddenly can make connections in your mind that weren't there before, that wouldn't even have been possible to make because you were missing essential parts. And actually, one of the blog posts or one of the things that motivated me to write this book or learn about compilers was a blog post by Steve Yaggy. It's called Rich Programmer Food. And he essentially says that you should learn about compilers. And if you're in college, you should take the compiler course. It's the most important course there is, because if you learn about compilers, you learn about all the things I mentioned before, the abstract syntax tree, you learn about lexing, you learn about parsing, you learn about traversing trees, you learn about code generation, register allocation, and, all these things which sound like you only might use them in a compiler, but as it turns out, you can use them everywhere. You can apply these concepts in a lot of different ways. And the best example I have is a programmer called Mark Bates. He read my book. He wrote a framework in Go called Buffalo. And he actually wrote the templating language after reading the book, because suddenly it clicked in his mind and he knew how to write a templating language before. And that was just, something far away. How do you even parse templates? How do you evaluate different statements in a template? How do you, evaluate conditions and so on? And, he learned about interpreters. He built the programming language Monkey, which seems fairly unusable in a day-to-day job, but suddenly he built a templating engine, which is, of course, something usable.
Is the Monkey programming language a thing that you made up, or is it a thing that's a real thing?
Yeah, it's a thing I made up. Yeah, I wanted to call it Tiger because tigers are my favorite animal, and then I looked at one of the compiler books sitting on my desk, and I realized that there's a tiger on one of them, and I opened the book, and on the first page it says, the language we're going to build in this book is called Tiger. And I thought, all right, so it's not going to be Tiger. And I like monkeys very much, so I called it Monkey. And it's, in my mind, it's the language that lives in a book. So there is no official implementation of Monkey. There are tons of implementation floating around on GitHub because I licensed the code under the MIT license. So, if you read the book, you can build your own Monkey interpreter as it is in the book and just share that or modify it or upload it on GitHub. And so the original version is doesn't exist. It only exists in the book, but there are a lot of own versions of readers in different languages even. People implemented it in Haskell, in Elixir, in Dart, I think in Java too. So yeah, it's a language with many faces. It's a small language, and not to, spoil a secret, but I'm currently still working on it and tuning it a bit, and I want to publish a few modifications in the future about how you can make Monkey even more fun.
So let's talk about this for a second. You've got Monkey, which is a pretend language, and in this book, it's not just writing an interpreter; it's writing an interpreter in Go, because of course you have to choose some language. You could have written it in C or Java or whatever. Right. What if the people who are listening are not Go programmers? Why would they? Does it matter if I'm not a Go programmer?
The reason I choose Go is because I think it's a language that's super easy to understand, even if you've never written a line of Go code in your life. That's something people complain about, that Go is too simple and it doesn't have all the, bells and whistles of modern programming languages, an elaborate type system or something like that. And it's essentially just a modern version of C. And that's exactly why I chose it for this book. First of all, I like programming in Go. I've been doing it for a few years now, and it's a great language. I enjoy using it, but I think as a teaching language, it's super well suited because there's not a lot of stuff going on you can't understand if you've never written Go. And I always compare this to Ruby, which I used for quite a long time now. And if I use Ruby, which is object-oriented and has meta-programming and has DSL stuff going on, and it looks like English, but if you look at Ruby code, some Ruby code, and you've never written Ruby in your life, you're going to have a hard time understanding it. So there's a lot of different things in the way between you and understanding how the program works. And if you look at Go code, even if you're a Java programmer or you're a C# programmer or JavaScript programmer, if you've ever used the curly braces language, I think you're going to look at Go and you're going to understand what's going on, because there is not a lot going on. And in the book, I do not even use like concurrency stuff. I don't use channels, and I don't use fancy libraries. There are no third-party libraries, actually, only the standard library. And I think, as I said, if you know JavaScript, for example, you're going to have not such a hard time understanding Go code, even if you've never written Go before. I mean, there's the hurdle, if you've never heard of pointers before, that might trip you a bit. But honestly, I don't think that's going to stop you from understanding the code presented, or that's going to stop you from translating the code to your favorite language.
So it sounds like you wanted a language that would get out of the way,
right?
And let you talk about the concepts, and that was Go. And the thing that I think is most interesting is your choice, as you've pointed out a few times, no third-party libraries. You really have the entire book contains the entire code of this interpreter. You're going to learn everything from Hello World main all the way through to your final application.
Exactly, and that's. I'm not going to brag, but I have to say that writing this interpreter for Monkey, which again is just 3,000 lines, that has been one of the most joyful coding experiences in my life. And that's not even relevant for the book, because I wrote the interpreter before, but I'm a guy who works with web applications all day. I have to start up a database when I want to work. I have to start up a second database when I want to work, and I maybe have to start a message queue, and I have to start a background job, and I have to start some JavaScript process that bundles my front-end assets or something like that. And I have all this stuff around, and I have third-party libraries, and I have to go read through documentation and readmes, and I have to understand how all these pieces fit together. And it's perfectly fine in a production environment. You get paid to do it, and you need to get results. But writing this interpreter without any third-party libraries, that was like a breath of fresh air, because you could just run your tests. For the whole book is written in test-driven development, and you can run the tests in under half a second, and you don't have to read through any documentation at all. You can just concentrate on the one page of code before you and the test set, says it's failing, and you can look at your code and you don't have to understand anything else. You can just tweak around with your own code, run the tests again and see if you made them pass, tweak around some more and they're green. It's like, what draws most people to programming, solving little puzzles. And that's just so refreshing and it's so much fun compared to, all right, why is this failing? It turns out I used the third-party library the wrong way and it accepts, a timestamp instead of a date or something like that. And it's all gone. You just can concentrate on your code and it's super, I don't know, I read some weeks ago that programming is like playing Lego without gravity. And that sounds fun. And I actually think that's the most fun part about programming, when you're just, building some castles in the sky. And in that moment, building an interpreter or compiler is kind of like this. Strings go in and maybe something comes out, but you don't have to depend on anything else.
Yeah, the way I like to phrase it is that building things like this or projects like this are finite.
Right.
You can hold it all in your brain. There's no dependency chain other than the language that you picked. You actually picked Go and used only the Go standard libraries and standard, data types. You didn't pull in any dependencies at all. So you could do this entirely offline, right? You could write this on a plane.
Exactly.
And there's a joy in a finite and understandable project like this.
Yeah, that's I don't know, that sums it up pretty well, that you can write this on a plane without needing anything else. You don't even have to have an internet connection. And I think everybody understands
It's a good reminder to people, because I think some of us will go and we'll write code for 5 years, 7 years, 10 years, and get wrapped up in our IDEs and in our use of Stack Overflow and in our third-party libraries, and maybe forget about these little tiny projects that might be a couple hundred or a couple thousand lines of code that are finite. And it's kind of healthy to stretch the muscles and do these basic exercises. So many people buy exercise equipment and then someone reminds them, you could just do squats and bench press and pull-ups, and that's basically your main exercises, deadlifts.
Right. Yeah.
Get back to basics. And it sounds like you're getting back to basics with this. One thing I want to ask, though, is you're building an interpreter, not a compiler. Maybe you could talk a little bit about what that means to people.
Right. The original goal was to actually show how to write a compiler, but with the approach I've chosen, that I show every piece of code in the book and that it's all test driven and I show the tests in the book, it turned out that, it takes a lot of pages and it takes a lot of space to explain a compiler in full. So this is a reduction in scope, basically. And as it turned out, I played with the idea around in my head and I juggled some bullet points around and made a concept for the book and how I could, get it done. And I think what I found is that this project is a small interpreter that shows you things you didn't know before, but you now know and you can learn more about them. Once you've done this, you haven't written a compiler, but you suddenly know what an AST is, and you're starting to think, all right, I guess I now know how a compiler would walk along this tree and generate some code of it. And I think that's very helpful. And I started to write a compiler after I finished the book. And, it wasn't a lot more steps because the fundamentals are the same. And people always say, start with an interpreter, which is easy to do, and then try to build stuff on top of it. And if I would have done it the other way around, start with a compiler or, some advanced compiler, bytecode compiler or a JIT compiler, you would get lost along the way because you wouldn't be able to, as you said, keep the whole thing in your head. Yeah.
So you've said a 3-letter acronym, or TLA, a couple of times. You said AST,
right,
an abstract syntax tree. So if I understand correctly, if you're making a compiler, you take that source code and you might scan it once or multiple times if you need to, and you make machine language that is going to be executed by the processor. But when you're making an interpreter, you take that source code, and are you executing it line by line, or are you making an abstract syntax tree and then you're executing that? What's the pipeline look like?
So there is no generic way to do this, but the one chosen in the book, which is the most, common one, I guess, is that we parse the source code. We lex it. That means we turn it into tokens, which are just, small pieces, that are not characters, but say something like, the function keyword or opening brace or closing brace. Those are tokens. And we get those from the lexer, and then we feed them into the parser. And the parser says, all right, you sent me the function token, the function keyword token. What I expect next is that you're going to send me an opening brace, because now you're going to give me the arguments or the function body, or you're going to give me that conditional or whatever. And the parser then accepts these tokens or rejects them. That's the parser error. And once it has all those tokens, it starts building an AST, that abstract syntax tree, which is, an in-memory data structure that represents your source code as a tree. And most people are pretty irritated by a tree representing source code, which I go into a fair bit in the book, because if you look at source code, it doesn't look like a tree to you. It looks like source code to you. And if you have no experience with trees or abstract syntax trees, you don't know how to represent it as a tree. So we go into that and we explain how the parser does that. And once we have the tree, we start interpreting it. And that sounds like a wise guy answer, but interpreting it means walking down the nodes of the tree, and actually evaluating them, doing what they're saying. So you might walk along the tree and it says, I have here an infix expression with two operands and one operator. The operator is the plus sign, the plus character, and the operands are the integer literal 5 and the integer literal 10. So how do you go about evaluating that? You look at it and you look at the operands and you add them together, because the operator is the plus. And if the operator is a minus sign, you're going to subtract one operand from the other. And then you're going to return that. And you can do this in a recursive way, which is super beautiful, and it works really well. So you walk along this tree and you always pass another subnode or a child node of this tree to the same function that evaluated the upper parent branch. And so you walk along this tree and evaluate every node step by step. And in the end, you evaluated the whole program, which means you interpreted the whole program, and suddenly, you build a working interpreter that runs your source code.
And when someone is thinking about an interpreter versus a compiler, sometimes they think about speed, and they'll go and say, oh, well, this is clearly not as good. It's because it's an interpreter. Interpreted is always bad. That's not fair to say, though, is it, that interpreter equals bad? In
general, no. Or nowadays, no. You could say that a tree walking interpreter is actually, without any optimizations, is probably the slowest form to write an interpreter, but that's looking at interpreters from the perspective of 2017, right? Because, and this is like a pet topic of mine, the line between compilers and interpreters nowadays, it's so blurry that you can't even tell them really apart. So modern interpreters, what they're doing is they're not only walking along this tree and interpreting it, but they compiled the node into machine code, just did this already, and then they're going to turn this thing that they evaluated into native machine code. And the next time they come across this node in the tree, they're just going to execute the machine code. So what they did was they compiled the node into machine code just in time and then executed it. And what you have there is a JIT compiler / a JIT interpreter, because it interpreted the abstract syntax tree, but it also compiled it and ran the resulting machine code. And then you have interpreters that walk the AST and they generate bytecode, which is some form of machine code for a virtual machine. And then they pass it to the virtual machine, and the virtual machine interprets, in quotes, the bytecode and runs it. So now, what do you have? Do you have an interpreter that outputs bytecode, or that evaluates the bytecode, or is it a compiler that outputs bytecode and your virtual machine is an interpreter that walks along those nodes, but instead of evaluating it? I mean, when you talk about the standard interpreter, what you mean is a tree walking interpreter that just goes ahead, without any optimizations and evaluates each node in the tree. And on the other hand, you have a compiler that walks along those nodes, but instead of evaluating it, it produces code that then executes the code it's supposed to run. So to take the example from before, where you had a node that says plus 5 and 10, the interpreter would evaluate this and output 15 on the command line or somewhere else. But the compiler would actually output machine code that executes 5 plus 10. And just to put one on top, compilers are so optimized nowadays that it wouldn't even compile this to machine code, but it would pre-evaluate this and just put, the 15 and the resulting source code. So then you have a compiler that's actually interpreting some nodes while it's compiling to machine code. So I don't think the distinction is that clear, or that, as you said, it's fair to say that interpreters per se are really that much slower than compilers.
Mm-hmm. So it seems like if the work being done is in any way repetitive, and the interpreter is smart about caching those machine codes that have been done before, then the interpreter could very, very much in a tight loop be competitive with anything compiled. But if the interpreter is doing new and fresh work for the first time every time, then it might be slower, and then it might be something to worry about. But for the most part, it doesn't matter as much as you'd think it does. Exactly.
And then you also have the use case. Think of JavaScript interpreters. They're running in browsers. So what you want from a browser is that you go to a web page and it starts executing your JavaScript code immediately. You don't want the web page to have a 10-second compile step, which compiles your JavaScript to super fast machine code if you have to wait 10 seconds for it to actually run. So you have to make some optimizations along the way, and you have to interpret some code up front and then compile it later on, and so on. And as you said, if you put in optimizations, caching layers, remove redundant code or stuff like that, you can make interpreters super fast.
Very cool. So people can check this out at interpreterbook.com. And from there, they can check out the ebook, which includes a Kindle version and a PDF version. Or if they want, they can buy a paperback from Amazon and get a full version. And you're in all the Amazons all over the world. Is there any Amazon?
Right. Yeah, I don't think it's available in India, but it's available in a lot of Amazon stores worldwide. Yeah.
And they can buy the ebook if they want to.
Yeah.
Brilliant. Well, thanks so much for chatting with me today.
Thanks for having me. That's been a real pleasure talking about this.
Very cool. This has been another episode of Hansel Minutes, and we'll see you again next week.